as I was mentioning last time, some functions are not differentiable. That means you can't take the derivative, or they at certain points, for certain values, the derivative does not exist. Some functions are not differentiable at certain points. And I described sort of a few different ways that that can happen. So I will just redraw these pictures that I drew yesterday. One way is if the function comes to a sharp point, it's not differentiable at that point. No derivative here. That's because basically the derivative is supposed to represent the slope of the tangent line. But at that point, on a weird graph like this, which has a point on it, there is no unique tangent line. There's no one single tangent line at that point. There's actually many ways that you could draw the tangent there. And so there's no coherent derivative at this point. And then the other way this could happen is if you somehow have a curve where the slope becomes straight up vertical at certain points, like right here. Here there's no derivative, but it's for a different reason. Like there actually is a tangent line there. It's just that the tangent line is vertical, which means it doesn't have a slope. You know, the slope is the rise over run, but a vertical line doesn't have a slope because there is no run to a vertical line. So right here, this line here has no slope, all right? Which means there is no derivative at that specific point because it's a vertical slope. All right? These are two ways in which a function can fail to be differentiable. That means there is no derivative, all right? And these two pictures that I just drew, they are actually continuous. So I will say some continuous functions have non-differentiable points. That is, individual points on the graph where there is no derivative for whatever reason. I wanted to see what would happen on, like, what do these things look like with ordinary equations? Like these kinds of pictures that I drew here, they can actually occur with more or less ordinary looking equations. So here's an example, not looking at the graph, but just with a formula. How about y equals the cube root of x? I'm going to skip some of the details here, but the cube root of x looks like the graph of this. You know, the graph of x cubed looks like this, right? And the graph of the cube root would be, you flip that kind of on its side. It looks like this. This is the graph of the cube root of x. And that one, the slope, maybe it doesn't look like it on my picture, but the slope really does go vertical at the origin on this graph. And so we would expect that there is no derivative at the origin at x equals 0. And in fact, you can demonstrate that without too much trouble. So I'm going to say it turns out if you take the derivative of that, so this is, I'll call it f of x, cube root of x. It turns out f prime of x in this case, this is, I keep on saying that we're going to eventually learn some awesome tricks for doing the derivative. This is going to be real soon. We're going to talk about them. If you use those tricks, you can take the derivative of this function without too much trouble. I'm just going to tell you what the answer is, just because I don't want to get bogged down with this. It's not that. Sorry, it's 1. No, it is that. It's 1/3 times 1 over cube root of x squared. It turns out that's the derivative of x of the cube root of x. If you know the fancy tricks, this is not hard to do at all. We will talk about the fancy tricks soon enough. Anyway, I will just have you notice what happens if I try to plug in x equals 0 here. F prime of 0 would be 1/3 times 1 over cube root of 0 squared, right? I plugged in 0 to the derivative. And what is that? Well, the cube root of 0 on the bottom is just 0. So this all would simplify just to 1 over 0. And this is a DNE, all right? So this, I'm trying to show you what would it look like in the equation if there's a non-differentiable point. This is one type of thing that you might see, which leads you to believe that it's not differentiable at a particular point. All right? So this is one thing that could happen. You could take the derivative, and then for whatever reason you get a DNE after trying to plug in one of the points. Even though the original function actually does have a value at 0, this is not a problem with the original function. It is a problem with the derivative. Right? Okay, and I had one other to show you. So this is an example where the slope goes vertical. What about a pointy little point? How about a pointy one? Maybe you could guess what example I'm going to do. Anybody have a favorite pointy function? Perhaps like the only pointy function you know? Yeah, the absolute value function. That's the classic pointy function. Absolute unit of pointy function. Am I using that phrase correctly? Sometimes I see that phrase being used in the social medias. I'm not always sure what things are supposed to mean. Anyway, this is a pointy point, right? Let's try, as we, like before, let's try somehow to work with equations and show that this is not differentiable at that point. Working with equations. Now, f of x, this is going to be a little weird. This is the equation, f of x equals absolute value x. And I would like to consider the derivative of that. Anyone who knows the derivative tricks? Do you know how to take the derivative of the absolute value x? The answer is probably no. That's not really one of the tricks that we talked about, is it? Well, we haven't talked about any of the tricks. But yeah, this absolute value x is a little not clear how we should proceed. But remember, the definition, we did talk about this, the definition of the absolute value of x is as a piecewise function. We do it in pieces. It's like this, right? Sorry, I didn't want to do this yet. I am going to write the piecewise eventually. Not yet. Really what I want to talk about is f prime of x, okay? It doesn't matter what I'm not going to break it into pieces, not just yet. Let's actually do the derivative using the definition of the derivative with the limits, because apparently nobody here knows the fancy trick for taking the derivative of the absolute value. There isn't really one, that's why you don't know it. Let's use the definition here. Remember the definition of the derivative? It's this. We've done several examples of this last time, and you did it on the homework with particular points plugged in. All right. This says lim h goes to 0. What do you think? What should I write here for f of x plus h? We should be plugging it into the function. What do you think? Yeah. Yeah, absolute value x plus h. Great. Minus f of x. F of x is just absolute value x. Okay. Divided by h, right? Unfortunately, there's not a lot that you can do with this right here. You might wonder, isn't there some rule about can I like add together the absolute value? The answer is no, you can't really. These things, the absolute value does not play nice with adding and subtracting things really. But really, when I look at the picture here, I'm really only concerned near x equals 0. So I would like to only consider f prime of 0, right? Now, I could have started with 0 at the beginning, but if I'm using 0 for x, it looks like f prime of 0. I'm just going to take what I had before, but use x equals 0. Now it just says absolute value h minus absolute value 0 over h. I used this and just plugged in x equals 0, right? Because 0 really is the point. I'm trying to look at this pointy point. So I'm going to focus on when x equals 0. And this looks like absolute value h over h. All right? Can you cancel the h's there? Just get. The answer is no, you can't. What are you going to be left over with if you cancel the h's? 11 on top? No. That was a joke. You get it? The two absolute value bars do not make 11 when you get rid of the h. You can't cancel the h in that case. What we can do though, here's when I went I got too excited before, but I'm going to do it in the pieces now. Remember the absolute value function? When h is positive, the absolute value of h is equal to h. So I'm going to say if h is positive, what this is just h over h. And when h is negative, it's minus h over h. All right? That's because the absolute value here, when it's positive, the absolute value is just the same as h. And when h is negative, the absolute value is the same as negative h. All right? So this is using the definition of the absolute value function. And then this, I can simplify each piece individually, right? The top piece is 1, and the bottom piece is minus 1. So the derivative here, f prime of 0 is, sorry, I forgot my limbs. There needs to be a limb out here. Sorry about that. I always hassle people for not writing the limb. Okay, 1 minus 1. All right. And I ask you, what do you get when the h approaches 0? The answer is this limit does not exist because there are two different answers that you would get when you plug in h equals 0 here. Approaching like h from the left, you would use the first formula. From the left, you would use the bottom formula, because that would be when h is slightly less than 0, and you get minus 1. But from the right, you would use the top formula, and you get 1. So here, this limit does not exist, because from the left, you would use the second formula, and you get minus 1. But from the right, you get plus 1. And that means overall, the limit does not exist. Which means the derivative does not exist, right? All along, this is trying to compute f prime of 0. So f prime of 0 does not exist. It's because you get two different values for the limit depending on which side you're approaching from. And that means overall, the limit does not exist. And actually, this is very clear. You can see this exactly on the picture. If I'm trying to talk about the slope of this graph, near this point, if I come in from the left, the slope is minus 1. If I come in from the right, the slope is plus 1. And that's exactly what we said at the end of this business, right? It agrees perfectly with the picture. So these are two examples of sort of fairly ordinary functions which have a point at which there is no derivative, right? Any thoughts about that? The moral is, it is possible for a continuous function to have no derivative at a particular point. I would like to talk for a few minutes about the other way around. So it can be continuous even though it doesn't have a derivative at a certain point. I would like to ask, is it possible to be differentiable but discontinuous at some points? Actually, that is not possible. So, sorry. This is a true fact, which I would like to explain a bit. Any differentiable function, that is, if the derivative always exists, any differentiable function must be continuous. That is, if the derivative exists everywhere, then the function is automatically continuous, all right? Although it is possible to be continuous even if it's not differentiable. But if it's differentiable, then it automatically must be continuous. I want to do, actually, a little proof of this. Would you allow it? I know some people don't like talking about proofs, but this is good practice for understanding sort of how to play around with derivatives and limits, all right? And a little good practice about just sort of how you prove things in general. You know, if you're a math major, you will eventually take our discrete mathematics course, which is really a whole course about learning how to logically prove things. You've probably done like simple proofs, maybe unsimple proofs in the past. Anyway, any differentiable function must be continuous. So what you got to do is we're going to we'll assume that f is differentiable at some point, let's say A. And then I want to demonstrate we'll show, proofs you use like real words. We're going to show that it is continuous. And I don't know if you remember, but I hope you do. The definition of continuous, it means lim x goes to a, f of x, equals f of a. Remember, this is the definition of continuous. It means as you approach a value along the curve, the actual value that you arrive at is the true value of the function. All right? The limit of the function is equal to the value of the function. This is what it means to be continuous. This is the definition of continuous. And it involves just kind of playing some tricks with the derivatives and such. So we're going to use this form of the definition of the derivative. F prime of a is lim x goes to a, f of x minus f of a divided by x minus a. This is the other, remember there were two different definitions of the derivative that you can use. One using, when I wrote this before I used a's and b's, but here I'm using a's and x, doesn't matter. And then the other is the one with the h, which is what we more often use, the one with the h. All right? Anyway, we're going to just start with this and try to end up with this. That's the goal here, right? This is what we know that f is differentiable, and we're going to just sort of shuffle stuff around in this formula and try to end up with that right there. What's the strategy? The idea is I'm going to rearrange this fraction over here, right? So, oops, this is a real sort of simple trick. Simple tricks. The fraction on the right side is f of x minus f of a over x minus a, right? But this, if I were to multiply times x minus a, of course, what you get is the thing on top, right? And what I'm going to do, so that is definitely true about the fractions. What I'm going to do is take the limit on both sides as x approaches a. So take lim x goes to a on both sides. And then use our rules about limits. Like if I have, so on the left side I have two things multiplied together. That's the same as taking the limit of each of those two things and multiplying the limits together. So the left will say lim x goes to a, f of x minus f of a divided by x minus a times lim x goes to a of x minus a, right? And the right will say lim x goes to a of f of x minus f of a. So I took the limit on both sides and I split up the limit on the left side. Remember we had that big list of rules for limits? You can split up a limit if you have a limit of two things added together or two things multiplied together. You can split it up, and that's what I just did. Oh, but these two parts, we're almost done with this. For those proof haters out there. What are those two parts? You can actually sort of simplify them. Can anyone say, what is the limit as x approaches a of x minus a? Anybody still paying attention? Remember how you would find the limit if there were like ordinary numbers in there? Was you plug in that value of x and see what you get. What did you get in this case? Yeah, it would be 0. If I were to do this limit, I would do it by plugging in x equals a, and then what you see there would be a minus a. Maybe I'll just leave it like that for now. That's going to be 0, right? And then times this part here. What is that part when I take the limit? Well, actually, that part is equal to the derivative, f prime of a. That's the definition of f prime of a, all right? And on the right side, I don't really know what to say about that. One thing you can do is just split apart this limit again. This is the limit as x goes to a of f of x, and then minus, it's really just that minus f of a. You don't even need to write the limit on the second one because the second one has no x in it. So you just get f of a by itself. But anyway, the left side is 0, right? A minus a is 0 times f prime of a, whatever that is, it's still going to be 0. So the whole left side is 0. 0 equals lim x goes to a f of x minus f of a. And then I'll just add the f of a to the other side. And this is what, ain't that what I said we wanted to demonstrate before? You look in the box way up there. You can't go all the way up there. That's what I wanted to show, right? I said before. We're going to show this. Lim x goes to a, f of x equal f of a. And that's exactly what we ended up with. It's the other way around. Good enough, right? That's the end. Sometimes people write a little QED, which is like a Latin phrase, meaning I done did it. What I said I was going to do, I did it. I have an old real analysis book, which this is like from the 19-teens. At the end of every proof, it says tune, which I kind of like. So I will write tune to indicate that I said what I was going to demonstrate, and then this is it. That's what I said I was going to show. So we did it. All right. This is a little proof about differentiable and continuous functions. So the moral of the story is, if the function is differentiable, it is automatically continuous. That's what this has just demonstrated. If it's continuous, it does not automatically mean it's differentiable, because we just saw like the absolute value function and some other things can be continuous even if they are not differentiable. All right. Any questions about all of that? All right. I can tell you guys are done talking about the proofs. That's all right. Let's talk about something completely different. And our last thing to say, almost last thing to say about our sort of general introduction to the derivative before we get to the fancy derivative rules and tricks. I would like to talk briefly about derivatives on graphs. What I mean by this is, we have done many examples finding the derivative of an equation by using that limit as h goes to 0 thing. You can also just look at the graph of a function and draw the derivative, draw the graph of a derivative. So you can do this whole thing without ever using formulas and just using pictures the whole time. Here's what I mean by this. Let's, I'm going to invent a nice sort of pleasantly nice looking function here. I will call this f of x. And your job is, let's draw a graph of f prime of x, the derivative. Can we do it? Yes, we can. Just by looking at the graph, all right? I'm not going to tell you the equation for that, and you're not ever going to use the equation. Just by looking at the graph, can you draw a graph of the derivative? Let's see if we can do this. I'm going to draw it directly beneath, and this is my suggestion to you, is that you draw the derivative directly beneath the original graph. Anyway, here's my suggestions for how to do this. I would say, first, identify where f prime of x equals 0. Look at the original graph, which is up here, and ask yourself, are there any points where the derivative equals 0? And the derivative, since you don't have an equation to look at, all you have to go on is the slopes. So I would like to know, when you look at this picture, are there any places along the picture where you see the slope is 0? Slope meaning 0 would be the tangent line is slope 0, which means a horizontal. Are there any such points? What do you think? Yeah, I see 2 such points, and they are like around here and here, right? Those are points where the derivative is 0. He said those are the minimum and the maximum points. They're sort of the mountain peaks and the troughs, the bottom of the valleys, right? Those are places where the derivative is 0 because the tangent line would be straight up horizontal. All right, first identify those points, and then also I would like to, once you've sort of isolated those points, also say when f prime is positive versus negative? Can you look at the original graph and say, like, on a certain region, the derivatives are positive, and on a certain other region, the derivatives are negative? In terms of the slope, remember, positive slope means it goes up as it goes to the right. Negative slope means it goes down as it goes to the right. So I would say, like, for instance, in the middle here, are these positive or negative slopes? The answer is negative, because it's going down as it goes to the right. So I'm going to indicate that. You can do this however you like, but I would say, like, I'll put an N there, indicating that the slope is negative. In fact, everywhere between those two big points that I marked, the slope is negative throughout that whole thing. Although, I would say it's like less negative over here. I'll put a little N, right? Like right around here, it's only very slightly negative. And then right at this point, of course, it becomes 0, so it's not negative anymore. Okay, how about over here? I would say over here the slopes are positive. And in fact, they are positive throughout, but they're becoming like increasingly positive as we go off to the right. So I'm going to indicate that by some P's getting bigger as we go to the right. All right, you can write this however you like. The slopes in that region are positive, and they are increasingly positive as we go to the right. And how about on the left side? Here they are also positive. Remember, you always say, as I move from left to right along the picture, is it going up or down? And the answer is it's going up. And if I were to talk about sort of how positive is it, it's like super duper positive over here because it's very steep, and then less so as we go over to the right. All right, this is my attempt to describe the slopes as we go across. And typically this is usually not hard to do, right? You just find the zeros first to help you kind of get a handle on things. And then in between the zeros, it has to be either positive or negative, depending on if it's going up or down. All right? Okay, let's try and draw our picture. So remember, my goal was to draw a graph of the derivative. I'm going to do that on the empty, axes down there. Down here is going to be my picture of f prime of x. I'm going to start by plotting. So what you want to plot here, the y values on the picture I'm about to draw, should equal these slopes. And it's not really possible to do this exactly, but for example, at these points, these zeros, the slopes at these 2 points are 0. That means the y values will be 0 on my picture that I'm about to draw. So I'm going to put a point there and a point there to line those are meant to line up vertically with the points upstairs where the slopes are 0, right? These points, the slopes are 0. And so when I draw the derivative, which is drawing the slopes, it should be 0 at those 2 points, all right? And in fact, those are the only points when what I'm about to draw is 0 only at those 2 points. It's not going to be 0 anywhere else. And now all you got to do is kind of like connect the dots or something. Like, for instance, between these 2 points here, there's sort of 2 choices. It could either go connecting them up like that, or maybe it does like that, all right? It doesn't do something silly like that because this involves other zeros in between, and there are no other zeros in between. So it's just got to be one of those. Anybody have a feeling about which one it is? The uppy or the downy? The one down there. Why do you say that? Yeah, because in this region, the slopes are negative, which means whatever I draw over here, it should not have positive values. It should have negative values, because what I'm trying to draw down here is supposed to equal the slope. So the correct one is that one. All right? Plot those 0 points, and then fill the curves in a way so that the y values of the curve here matches the n's and the p's up here. All right? So over here to the right, it's all p's, which means what I draw down here should be all up here on the positive half in terms of the y values rather than down here. And what I see here is slightly positive, becoming increasingly more positive. So I want to draw a curve that does the same thing. It begins off just a little bit positive, and as we go to the right, it becomes increasingly positive. Can you see in your mind what that would look like? Or on the paper, perhaps? It should just look like that. It starts off, it's always positive. It starts off being sort of a little bit positive and becomes more and more positive. All right? And then on the other side, we're almost done here. This part. the leftmost portion is super positive, and then it becomes less and less and less positive, and eventually 0. So it looks like that, right? It starts off being super duper positive, becomes less and less positive until it hits the 0. This is a graph of f prime of x. All right. What do you think about that? Anybody got any questions about this? If you're used to thinking of the derivative in terms of equations, you will notice that the first curve I drew looks like a cubic, and the second one looks like a quadratic, which, if you know the trick for the derivatives, that does make sense, right? That is what it's supposed to do. Although I didn't use the trick at all, right? This is just looking at one picture and drawing the derivative of that picture. All right, I'm going to do another one, and then I got some for you to try. I like these problems just because they are a nice change from the sort of drudgery of the limit as h approaches 0. Like that thing, as you know, I'm sure, that thing kind of gets old after you do that a whole bunch of times. This is another way of talking about the derivative, which doesn't involve kind of endless, distributing and factoring, which can get old. How about, I'm just going to draw a super curvy, something like that. And let's make the end here. Let's just say it ends like that. All right, can we draw the derivative? I'm going to try and use the same strategy. My strategy is, first, look for places where the derivative is 0 on the original picture. That would be like the mountain peaks or the valley, whatever points, the bottoms, the tippy tops and the bippy bottoms. All right, something like that, right? I see 4 of them. Those are points when the derivative is going to be 0. So when I draw the derivative, it's going to be 0 here, 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 and here. I'm trying to line them up vertically. And now I got to connect the dots with curves that either go sort of up above the x-axis or they go down below the x-axis. And how you decide is based on the slopes from the original picture, be they positive or negative. So if you want, I could put in my p's and n's. That part is positive, that part is negative. This part is positive, this part is negative. It's all about, is it going up or down as you move from left to right along the picture. This part, I guess we get a little bit of positive at the end there. All right, and then downstairs in my answer, I'm going to try to connect the dots here. Say for these 2 dots, really the only thing that could be is either like that up there or like that down there. Which one should it be? The down one, right? Because you see that n on this interval. So I'm going to use the one down there because the slopes are supposed to be negative. What I'm drawing is the slopes, so what I'm drawing has to be negative. All right. The next bit is going to be positive between those 2 points, so I should go on the positive side, right? The next arc should be negative, so I go on the negative side. And then finally, a little bit of positive, look something like that. And on the far left side, another little bit of positive, look something like that. So this is my graph of the derivative of the original. Right? What do you think? Any questions about that? This is drawing the graph of the derivative. Sometimes people look at these and ask me something like, isn't that just like the same as the first picture but upside down or something? You just like do the opposite each time or something? And my answer is no, it's not really like that. You may, if you look at enough examples, you might convince yourself that there's some kind of shortcut reasoning that will allow you to just easily translate this one picture into the other. But really, there are no tricks to this. You have to actually look at the original picture and think about the slopes. Like you will see, I would agree on that picture. It does kind of look like you just turned it upside down and maybe moved it over, but nothing like that happened in this example, right? It really, your answer will be a totally different picture. Sometimes it might look similar to what you started with, but that should be regarded as just a coincidental. All right, I got 2 for you to try. See if you can. I'll try and draw them. There's 2 separate ones to do. I'm going to draw them side by side because I like to put my answer vertically beneath. So one is like this, and the other is like this. Here's a little tricky trick. This one has a horizontal asymptote. As it goes off to the right, it just approaches that specific y value. You have to think a little bit about that one, because the examples I didn't involve something like that. But see what you think. I will give you a few moments to try them out. All right, let's talk about these just because we got to go soon. I had one more thing to get to today. Some people have disobeyed my advice to draw your answer vertically beneath the original picture. It's a lot easier that way, although, you know, it's a free country, as I always say. It looks like pretty much everybody worked out the first one there. You mark these points off. They are the points where the derivative is 0, which means in my answer will go through y equals 0 at those points. And then the positives versus the negatives, it's positive here, then negative, then positive, then negative. So what I draw downstairs should start off positive, and then negative, and then positive, and then negative. So I hope that's what you got. Anybody have any questions about that? That's good for the first one. Okay, and the second one. I will again start by marking off points where the derivative is 0. I see only one such point right here. All right, that is a point where the derivative is 0. I saw actually a lot of people put a dot around here somewhere. That is not a point where the derivative is 0 because the tangent line right there is not horizontal. It's still, slanty like that. I would say because this is an asymptote here, the slope never actually reaches 0 again, right? It gets very close to 0, but the curve here gradually sort of in the limit, you could say it totally flattens out, but actually the curve itself never becomes totally flat. So this is my only 0 here. What I see here is something which is negative becoming 0 and then positive. I would say it's quite positive here, but then like very, very slightly positive, becoming close to 0 as you go out to the right, but never actually equaling 0. That's how you should interpret this horizontal asymptote. As the curve goes out to the right, the slope is going to be positive the whole time, but it gets very close to 0. So that's what I'm going to try and draw down here. First of all, this 0 point gives me a point right there, and I need it to be to the left negative, so it should start off like that. And then to the right, this is like the interesting part. What you want to draw is going to be quite positive to begin with, and then only very, very slightly positive and getting really close to 0 as you go off to the right. So something like this. Like that. All right. It is positive throughout, and as you go off to the right, the slope is getting is approaching 0 in the limit as you go off to the right. All right. Any thoughts about that one? That's a little tricky, but we can handle it. All right. Excellent. Just a few simple things to say before we go. We've got 5 minutes. There's enough time to say a few simple things. So one thing is very simple, and that is just there are various notations for the derivative. That is, different ways that we write the derivative. So for, if I have an original function which is called y, or f of x, how do we write the derivative? We write the derivative as, you could write f prime of x, that's usually how we're going to write it. Although in certain contexts, it's written in other ways. And another way this is written is like this, dy over dx. And that looks like a fraction, although it's not really a fraction. It just means the derivative of y, which is the same as f of x. This is another way of writing the derivative as dy over dx. And I'm just going to say this is not really a fraction, because you don't, for instance, cancel the d's or something like that. You should not think of that as being a fraction. It represents, this is like a special way of writing the derivative. It represents the derivative, and why do we write it so that it looks like a fraction if it's not really a fraction? It's because this is a way that, this is an appropriate way to write it if you are thinking of the derivative as a slope of something, which it is. This is meant to resemble the fraction that you get when you do the rise over run. And when you think about the rise over run, the rise means the change in the y value, and the run means the change in the x value, which is what these d's are supposed to connote, right? It's what the idea that you're supposed to get when you see this dy over dx is that this represents the rise over the run of your function. All right, this is called the Leibniz notation. Leibniz is like the other guy who invented calculus. Newton and Leibniz kind of came up with all the basic ideas on their own separately. And they had different ways of writing it because they were working separately on their own. One other way, or sometimes it's written this way. If you want to do that like dy dx kind of thing, but you don't want to say y, you want to say f of x, it's sometimes written like that. D over dx of f of x. This is a weird, in my opinion, but this is the derivative, the derivative of, is what I'm trying to write here. The derivative of. So when you see like that thing right there, it as an operation means the derivative of. That sounds like an incomplete sentence because it is, right? It's the derivative of f of x is the thing that you write after it. So this d dx is writing the derivative as if it were an operation. So for instance, it is a fact that like the derivative of x squared equals 2x. I happen to know this. The way you would write that is like this. This means the derivative of x squared is 2x, right? D over dx, as an operation, it means do the derivative of whatever comes after it, right? What do we got? We got 2 minutes. I think that's a good place to stop. Next time we're going to say a little bit about the higher derivatives, and then we'll talk about the awesome tricks. Next time we do have our quiz. As usual, it's based on the homework that's due today. See you then. Let me know if you got homework questions. I can try to help.